Okay, so this is section 4.1. We are talking about rational functions, okay? So we've got two definitions up there. One of them is a rational expression, and one of them is a rational function, okay? The first one is actually our rational expression. So let's go ahead and write that down. That's way too large. This is probably going to be way too small, isn't it? No, it's not. Okay, rational expression. Okay, and that's just a fraction that is the quotient of two polynomials. Okay, polynomials meaning things like x squared plus 2, 5 is technically a polynomial. Okay, it's just a monomial, but yes. And then below it is actually a rational function. Which takes all of those rational expressions and puts them together to form a function. So some examples that we're actually going to see today. Also, this f of x stands for function notation. If you guys haven't seen that before, a lot of times you'll see things in like y equals, but this is f of x, so it's just a different way of writing it. You might see, whoa, how did it change that small? Okay, f of x equals 1 over x is an example of a rational function. Or you could see something like, I don't know, x plus 1 over 3x squared minus 5. Anything that can be written as a fraction with things on top and bottom. Okay? All right. We also need to talk about two definitions, an even and an odd function. Pretty straightforward. Even numbers, even function. Odd numbers, odd function. In terms of exponent is what I mean by that. So I'm going to go ahead and write this over here on the side. And I'm going to write an even function is something like x squared, like we were talking about on the warm-up. So like y equals x squared. It's considered an even function because it is symmetric about a vertical line. Okay, so symmetric. Okay, that vertical line might also be a vertical asymptote, which I'm going to abbreviate with VA. Have we seen that notation before? Yes? Perfect. Okay, and then our odd function would be something like y equals x to the third power. Anyone remember what that looks like? So it kind of looks something like that. It's not perfect, but that would be x to the third. So, and this obviously is not symmetric about a line. This would actually be symmetric about a point. Okay, we're going to talk about the parent function, f of x equals 1 over x today. Okay. Let's go ahead and go to Desmos, or if you have a graphing calculator, grab your graphing calculator out, and I want you to go ahead and graph 1 over x and see what it looks like. So I'm going to go ahead and label an x and a y chart. And I want you to have at least 2 points, and you'll kind of see why I choose 2, because you're going to figure out, what the end behavior is going to look like. Okay, so if you at least have 2 points, in this section we're mainly looking at like domain and range, which you'll be able to tell looking at the asymptotes. So let's just go ahead and pick easy numbers like -1, 0, and 1. We already talked about what happens when you plug in 0. It's going to give you an undefined. And then some pretty easy math here. 1 divided by -1 gives me -1. And then I would get 1 over here on the other side, okay? Now, here is where notability is way better than explain everything, because I'm going to try and draw a dashed line, and it's not going to look very nice. So that's okay, though, because I'm going down the y-axis, because I've got one asymptote on the y-axis, and I've got one asymptote on the x-axis. And then I'm just going to plot those 2 points. I've got the point -1, -1. And I've got the point 1, 1. Okay, and if you remember on the graph that we just looked at, the end behavior is always going to be the same. It's always going to look the same way unless there are transformations happening to it. So I'm just going to go ahead and sketch myself a little picture here. It does not have to be perfect. But the main thing here is, can I ever cross the asymptote? No, okay? Wonderful. Domain is going to be all of the x values that make this function true. Okay? What's the only value that I can't have for x? What? 0. I cannot have 0, right? So we're going to write our domain in terms of interval notation. Okay, so if you weren't sure what domain was, go ahead and write yourself a little note here. These are all of your x values. And your range is going to be all of your y values. So looking from left to right, I am starting all the way over here at -infinity, and then stopping at what point can I not have? 0. So I would write this as -infinity.
Do you care about the union?
Not really. So you can write it a few ways. You can write -infinity to 0. You can put the u. You can put a comma. You can put an and sign. They all truly mean the same thing. If it was like an AP test, they would accept any of those also. So any type of notation works for me, okay? And then I can't have 0, which is why I have that parentheses, but then I also go all the way to infinity. So I would have included 0 to infinity. So there's 2 parts of that graph. Okay, then my range is going to be all of my y values. And so if I look at all my y values, start at the very, very bottom here, I'm going forever and ever and ever down. So that means -infinity. And I stop again at 0, but then I go all the way up to infinity. So my range is actually the same here. So -infinity to 0 and 0 to infinity. Okay, so now that we know what the parent function looks like, we're going to be able to do a bunch of transformations like we had talked about before, okay? So let's fill in that definition here, definition of an asymptote. We've already talked about this. Okay, that's a line that will never intersect, a line of a graph that will never intersect, not part of the graph, but help describe a function's behavior, okay? It actually sometimes intersects, but not very frequently, okay? So let's go ahead and look at some of these. Let's skip this first one, okay? And let's look at the second one. I lied, actually. I want to do the first one and skip the second one. There we go. Sorry if you already marked it off. Okay, so I've got -2 over x is what I want to do. What is this -2 going to do to my graph? It's going to do 2 things, right? The negative part, I'm going to rewrite it like this. -2 times 1 over x is the same kind of thing, right? Just written a little differently. That negative is going to be that horizontal flip, right? It's going to flip horizontally. And what does that 2 do? Vertical stretch. Now, let me rephrase that question. What is going to be affected by this? Is any of my asymptotes going to be affected by a stretch or a flip? Are they going to shift at all? No, my asymptotes are going to stay the exact same. Okay, so since I know that this is a 1 over x parent function and it's just having transformations on it, I can go ahead and graph on the x and the y axis. I can plot my asymptotes. But then instead of it being in the first and the third quadrant, like it was for that first example, we are flipping it horizontally, which means we're going to be in the second and the fourth quadrant, right? Okay, so let's just pick a few points, X and Y. I either need to see a table with the points on it, or I just need to see the points drawn in the graph, whichever kind of works for you. But I know I've got some visual, I'm kind of a visual learner, so I like to have it written down before I actually graph it. So I'm going to just pick a few points, again, -1, 0, and 1. And if I plug that back into my original function, I would get +2, still an undefined, and then I would also get -2. And since I have a point for each quadrant, now I can just graph it because I know what the end behavior is going to look like. So on the left side in quadrant 2, -1, 2 is a point right here. And I know it's going to go really close to the y-axis, and I know it's going to get really close to the x-axis, but it's never going to touch. And then same thing in that fourth quadrant there. I'm going to go over 1, down 2. Never going to touch the y-axis, and also never going to touch the x-axis. Why don't you guys go ahead and write down what the domain and what the range would be for this function. Okay, try writing it out. If you're not sure, talk to the person next to you. So again, we are starting all the way on the left of my x values as -infinity. I can't be at 0. But then I can also be 0 to infinity. Okay, my range, is it the same? You betcha. I'm starting all the way down at -infinity up to 0, and then 0 to infinity. Okay, before we go to the next page, I want to talk about increasing versus decreasing functions, okay? So I'm going to color code, I don't know, let's do blue for when it is a increasing function. And I'm going to do red for decreasing. Or whatever colors you want to do. That's just what I'm going to do. All right, so let's go back here to the first picture of 1 over x and decide, is it increasing or a decreasing function? As I look from left to right, what is happening with my my y values here? They're decreasing, right? Okay, so this will be, yes, you are correct. This is decreasing. So decreasing is red. Not the gray there, okay? That is a decreasing function. And then if I look on the second half of the graph from left to right, my y values are getting smaller, so it's also a decreasing function or decreasing interval of that function. Now, since we did some transformations to the second one here, let's see what happens if it's decreasing or increasing. If I look on the left-hand side here from left to right, as I increase my x values, what is happening to my y values? Increasing. So this is going to be blue on my stuff. That is an increasing function. And same thing below. This would also be an increasing function. So now that we know the definitions of increasing, decreasing, even, odd, now we're ready to move to the second page and talk about synthetic division. So we're going to use synthetic division and translations to graph this thing. Okay, we're not just going to pick and plot points. We're going to actually make it so that we can use transformations. So write in here synthetic division, because if we go over this example and it's still like, I mean, we're not going to go super in depth on it, obviously. This is something that you guys have learned before, but you can look up synthetic division on any sort of device and it will give you a million videos to watch on how to do it, okay? Or you can come talk to me at some other time and we can go over some more examples. So we need to go ahead and divide these two things, okay? I'm going to take this x plus 2 divided by x plus 1, and I'm going to use long division or synthetic division in order to solve. Actually, this is long division. Synthetic division is without letters. I've said that to every single class and no one's caught me on it. This is long division. Synthetic is like with only numbers. So like it would be like 1, 1, and then like 1, 2. Yeah, so never mind. And actually it's written like this or something. Yeah, sorry. Big mistake on my side that no one caught until just now, and it was me. So okay, anyways, long division, I'm going to put x plus 2 on the inside here. Okay, so you're looking at the first term here. I've got an x. What can I multiply that thing on the outside by to give me an x? 1. Okay, so I'm going to put a 1 on top. Now I'm going to multiply these things together. 1 times x plus 1 gives me x plus 1. Now, if you think back to when you did long division in elementary school, what do you do with those two things after you've multiplied? You subtract them, okay? You subtract the whole thing. Or what I like to do is I like to just change the signs. And then I add, because adding is more fun. Okay? But feel free to do whichever way you want. Because now when I add these things together, do I have any x's left over? Nope. And then I'm going to have a positive 1. So this is my remainder. But I don't just want to have one remainder 1. Okay, it's not just a remainder of 1. It's actually a fraction. What would be the denominator of that remainder? X plus 1. Okay, the thing on the other side. Okay, so my answer, or what I'm going to graph, is y equals this 1 plus my remainder of 1 divided by x plus 1. Which you guys actually know how to graph. You might not think you do, but you do, okay? Because I have 1 over x, right? What are the two transformations that are happening here? What does this plus 1 do on the outside? Moves it up, moves the whole entire graph up 1, okay? Asymptotes and everything. So vertical shift of everything up 1. Okay, what about that plus 1 there? That's with the x. Think about it like being in parentheses. It moves left 1. Yes, so that's a horizontal shift. Left 1. Okay, so let's go ahead and start with our asymptotes here. Normally our asymptotes for this are at x equals 0 and y equals 0. Okay, but we're shifting that up 1 and left 2. So my asymptotes are going to be actually, the vertical one is going to be going through what x equals 1, negative 1, sorry. So x equals negative 1 because it's a horizontal shift. And then a vertical shift up 1 would mean shifting my entire line of y equals 0 up 1. Okay, make sure you're always using dashed lines for those asymptotes. Tells me we cannot cross them. Okay, and now that I have both of my asymptotes drawn, I just need 2 points at least, okay? So rule of thumb, pick a point on the left of the vertical asymptote and on the right of the vertical asymptote, and then you will get your 2 points. So if I choose, let's see, I'm going to choose negative 2 because that's on the left, and then I'm going to choose 0 to plug in because that's on the right side of my asymptote, okay? Again, we are only really caring about domain and range, increasing, decreasing, and even and odd functions, so it doesn't have to be perfect. Okay, so if I plug in negative 2, you can either plug it into this form or you can plug it into the format you got after you divided. I'm just going to do the first form there at the top. So if I plug in negative 2, that would give me 0 on top. So what is that going to give me? 0, right? If I divided it by negative 2 plus 1, it would still give me 0. So I can plot a point at negative 2 comma 0, and I know that my graph is going to look something like that. I can figure out my domain and range from that. That is enough information. Okay, if I plug in 0, 0 plus 2 over 0 plus 1, that gives me 2. So at 0, I plot a point at 2, and I go ahead and draw in my end behavior shape. Okay, now all we got to do is write our domain and our range. Next thing we're talking about is the parent function y equals 1 over x squared, or in function notation f of x equals 1 over x squared. So if we look at this function here, we're going to go ahead and graph it on whatever graphing calculator you've got. If it's a handheld, wonderful. If it's Desmos, that's fine too. Go look at what does 1 over x squared look like. All right, so I'm going to choose a few x's and y's here. Again, you don't have to choose many. At least 2 would be ideal. And since I know my horizontal asymptotes and my vertical asymptotes are still at the same spot as my original function for 1 over x, let's just go ahead and pick -1 and 1. Okay, when we plug in -1 into my function, 1 divided by -1 squared, the -1 should be in parentheses when you are evaluating that following order of operations. That gives me what? Just 1. What about when I plug in 1? 1. A lot of 1s going on. Okay, so on our graph, let's go ahead and draw our dashed lines for our asymptotes. And plot our 2 points. -1, 1, and 1, 1. And then go ahead and sketch your end behavior. You know you're going close to the y-axis and close to the x-axis. Okay, now domain and range on this one's going to be a little different. Which one is going to be different? Range, right? Because we're not in the negatives there, okay? Which makes sense because if I plug in any number into this function, if I plug in any value for x, you're going to square it. And if you square any number, it's always going to be a positive, right? So if I look at my domain will actually stay the same. From left to right, my x's go from -infinity all the way to 0. And then from 0 all the way to infinity. It just cannot be 0, because if I plug in 0 in for x, you get 1 over 0, and that is undefined. Okay, what is the lowest value my range can be for my y's? 0, and it goes all the way up to infinity. Okay, now would be another good time real quick for us to talk about increasing and decreasing functions. So that's with your color-coded, whatever you chose for increasing or decreasing. As I look on that first picture on this page, from left to right, what is happening on the left side? As I go from left to right, are my y values increasing or are they decreasing? As I go from left to right? Sorry, I did jump back a problem, so that might have been confusing. It is decreasing, yes. Sorry, that was a little confusing. Just making sure, keeping you on your toes. Okay, so it is decreasing here for the first one on that page. This is decreasing. And then what about the top right? As I go from left to right, are my values increasing or decreasing? They are decreasing.
Are they always going to be the same? Your parentheses?
Yes. If it's 1 over x. However, now 1 over x squared, they're not going to both be the same thing because it's now in quadrant 1 and 2, or it's going to be in quadrant 3 or 4. So if I look from left to right, what is happening to my y values? Increasing, right? So I'm going to use blue for that one. And then as I go from left to right on the first quadrant there, am I going to have increasing or decreasing y values? Decreasing. Okay, and again, would this be an even or an odd function if it's symmetric about the vertical axis there, or the y-axis? It would be an even function. All right, we're gonna go ahead and skip this next problem and finish it off with example 5 before you get time to work on your homework. Okay? So this is in the parent function notation of 1 over x squared, except for there's something happening with that x squared. We got a plus 2. What does the plus 2 mean if it's with the x? Left 2. So horizontal shift left 2. And then that negative 1, that is going to be what kind of shift? A down vertical shift of 1. Down 1. Okay, so my axis, or sorry, my vertical, what am I saying? My asymptotes are going to shift left 2, down 1. Okay, so I always like to draw those in first. So I'm going left 2, so that means I'm at the line of x equals 2, negative 2 specifically, and I am at the line y equals negative 1 for my horizontal asymptote. And then we just got to pick 2 points. Okay, what 2 points would be good points to pick? Negative 3 and negative 1, because they're on the immediate sides of that vertical axis. Okay, and when I plug those back in, this one's got a little bit more in depth. Plug in your calculator, think about it real quick here. When I plug in negative 3 for x, what am I going to get for y? 0? Do we agree? And what do I get when I plug in negative 1? Does that make sense that they're the same? Because they are symmetric, right? So over negative 3 at 0 and over negative 1 at 0, my end behavior is going to look the same. So I'm going up close to the y-axis and close to the x-axis. I'm going up close to the y-axis and close to the x-axis. And then our domain and range have obviously switched. Cool, so we got to list our domain and range. Domain and range. So domain, all your x values. What can x not be? Negative 2, right? So you're going from negative infinity all the way to negative 2. And then from negative 2 all the way to infinity. Bless you. And then my range, my smallest range, or my smallest y value, is negative 1. And then I can go all the way up to infinity.